Hello, welcome to this video. In this video, we'll be looking at higher derivatives. Higher derivatives are simply looking at, further differentiating more. So we have the function y given by f of x. When we differentiate this, we get dy dx, and we can write this as, f prime of x. Now, what if we differentiate this further? What if we differentiate dy dx? We're allowed to. It's not like we can't be allowed to. We get f double prime of x. But you could also write this as, which we read as d2y dx squared. Now say, for example, we have the function y is equal to x squared. We know that dy dx would be 2x. Now d2y dx squared is going to be differentiate 2x with respect to x, you get 2. d3y dx cubed is going to be 0 because if you differentiate 2 with respect to x, you get 0. Now, there are numerous applications of higher derivatives, and we can start with a few. One is in motion, for example. I'll just illustrate that on the previous slide before we get into that example. We know that acceleration is equal to dv dt, and we know that velocity is equal to ds dt. So acceleration is in fact the derivative with respect to time of the derivative of displacement with respect to time, which you could write as d2s dt squared. Okay, let's try an example then. So given that velocity is equal to 3 times 4 minus s squared to the power half, show that a acceleration is equal to negative 9s. Now what do we know? We know that velocity is equal to ds dt. What does that mean? Since velocity is equal to, I can write this as 3 times the square root of 4 minus s squared, okay? So since velocity is equal to this, that means that ds dt is equal to 3 times 4 minus s squared all under square root. Now, acceleration is equal to dv dt. That means I have to differentiate with respect to time, velocity. But what's velocity? The velocity has been given as 3 times 4 minus s squared under square root. So that's what I'm differentiating with respect to time. Now, from the chain rule, we know that to differentiate this, since it's a function in terms of s, I'll first differentiate this with respect to s, so the derivative of 3 times the square root of 4 minus x squared with respect to s, and then multiply this by ds dt. Now differentiate this with respect to s. What would I use? I'm still going to use the chain rule, because this is, if I just write it aside, 3 minus 4s squared to the power a half. If I bring the power in front, it becomes 3 out of 2 times 4 minus s squared to the power negative a half. But then multiply by the derivative of what's inside the bracket. What's inside the bracket? The derivative of that is negative 2s. Now that 2 is going to go with that 2. So that this is simply negative 3 times 4 minus s squared to the power negative a half times s. That's going to be negative 3 times 4 minus s squared to the power negative a half times s. And ds dt already saw was 3 times 4 minus s squared to the power a half. So you can see that when you actually simplify that, you get negative 9s. And so we have shown as required. Now, we didn't exactly use, higher derivation there, but the knowledge that, acceleration is the second derivative of the displacement comes in handy to solve this. Okay. Now let's look at a question like this, which involves even a parameter. So x is this and y is that. Find dy dx. and d2y dx squared in terms of t. Now from this, we already know that we can get dx dt. A is a constant in this case. So dx dt is simply going to be 2at, since you can see that when you expand this, you get at squared minus a. A is a constant. Differentiate a with respect to t, you get 0. So dx dt is just going to be 2at, and dy dt simply going to be 2a. Now, how do we get dy dx? We know that dy dx simply dy dt multiplied by dt dx. By dt dx is the reciprocal dx dt. So this is going to be 2a multiplied by 1 out of 2at, which is 1 out of t. So we found the first part, dy dx, in terms of t. Okay, so how would we get d2y dx squared? We know that d2y dx squared is simply the derivative of dy dx with respect to x. And so we're differentiating with respect to x 1 out of t. Now, how do we differentiate 1 out of t with respect to x? This is a function of t. So we first differentiate this with respect to t, and then multiply by dt dx. Now this is the same as t to the power -1, which when you differentiate with respect to t, you should get -1 out of t squared. And dt dx is simply the reciprocal dx dt, which is 1 out of 2at. And therefore your answer here will be -1 out of 2at squared. And that's how we use further differentiation even while dealing with parameters. Okay, now how about for a question like this? We've been given the function y is 1 out of 2 minus x, and I've been asked to prove that this expression is true. So what do we do? There are many ways you could go about this. You could simply start by computing dy dx and then computing the 2y dx squared, and then calculating what the left-hand side is and showing that it's equal to what the right-hand side would be. But you can be smart about this by making observations along the way. Y is equal to 1 out of 2 minus x. This is the same as 2 minus x to the power -1. This should mean that dy dx is -1 times 2 minus x to the power -2, which is simply -1 out of 2 minus x squared. But then we did multiply by the derivative of what's inside the bracket, which is -1 by the chain rule. Shouldn't forget that. So that means we'd have to multiply by -1 here, which is simply 1 out of 2 minus x squared. Just by comparing dy dx with y, you can see that this is y squared. So dy dx is in fact y squared. That's a keen observation that is going to actually help us to reach our proof. Now the 2y dx squared is going to be equal to what? When you differentiate 1 out of 2 minus x, squared with respect to x, what do you get? Simply going to be the derivative of dy dx. Now you could choose which expression to go with. Do you want to go with 1 out of 2 minus x all squared, or you want to go with y squared? Now, you could go with this, but look at what we want to prove and see which would be, easier for you or more beneficial to the proof. If we go with, okay, y squared, this means that we differentiate first with respect to y, and then multiply by dy dx. So the second derivative of y with respect to x is in fact 2y dy dx. Now look at what we want to prove. We have the 2y dx squared on the left-hand side, and we have the 2 on the right-hand side, as we would want. Okay, what's missing? We need to multiply by y to get the exact left-hand side of our proof. So if we multiply both sides by y, we'll have this being equal to 2y squared dy dx. But you know that our y squared is in fact dy dx. This will simply be 2 dy dx squared, which is what we're asked to prove. And so we'll have our completed, our proof. And so that's how we use, further differentiation, knowledge of second derivative, to solve questions like that.